Right, well, it's dead on 12:30, so I think we'll kick things off. So thank you very much for all of you coming along and joining us for today's webinar from the IMechE. Session today is the mechanical power transmission and the joy of gears. Just as way of some introductions here, my name's Dan Sanders and I'm the moderator for today's session. I work for the L&D team at the IMechE. And it's probably worth pointing out that as well as providing these webinars, there are many other training programs and courses that we run for both individuals and organisations that we continue to deliver both in a virtual and face-to-face setting. And I'll be keeping you updated throughout today's session with web links for future programs and courses and webinars that we think you may possibly be interested in. So just a couple of housekeeping points before we kick off. If anybody starts to experience any technical difficulties or issues, please put a message into the attendee chat box and one of our team will be able to respond to you directly and hopefully be able to resolve the problem. Secondly, in terms of Q&A, we're hoping to have some time at the end to answer some of your questions after our presenter has finished. If you can, please put any of your questions into the chat box all the way through during the session, and I'll be collating them and feeding them back to our presenter at the end, and hopefully we'll get around to answering as many of them as possible. Anyway, without further ado, I'd like to now bring in to our presenter. We're delighted to have Graham Penning join us today. He is the chairman of the British Gear Association, as well as a visiting professor of practice at the Newcastle University. So Graham, I'm now going to hand over to you.
Okay, thanks Dan, and welcome again everybody to today's webinar, Mechanical Power Transmission and the Joy of Gears. First, a little bit more of background. I started my engineering career in January 1973 when I joined David Brown Santasalo, and at that time David Brown had many engineering factories, and in the UK it had Vosper Thornycroft shipbuilders, it had David Brown tractors, and perhaps most famously Aston Martin cars. However, I started my career as a stress analyst at the Huddersfield headquarters, where they made every sort of gear and gearbox. And gearboxes you could hold in your hand to over 200 tons in weight. So I thought at the time, well, in 2 years I'll know everything there is to know about gears and gearboxes, and I can move on to something a little more exciting perhaps, like warships, tractors, or even sports cars. But here I am nearly 50 years later, still learning something new about gears every week. I'm still fascinated by this subject, and I guess that's today's mission. Whether you like it or not, in the next hour, I'm going to spread my fascination for the subject of gears and mechanical power transmission and hope to give you the enthusiasm I have. So 1 hour isn't a great deal of time, and so let's start. Let me tell you what we're going to do today. First of all, I'm going to give a little history of mechanical power transmission and confirm why it always has been and always will be critical to our way of life. And then talk about the development of the first engine and what we used to call the Industrial Revolution, but now we call the first Industrial Revolution, Industry 1, and how that increased the demand for mechanical power transmission. And then this led to further engines, mechanization, and these were developed. And this was Industry 2, mechanization. And this is where mechanical power transmission became even more important, and gears themselves became incredibly important. And then we have the revelation of why gears are such a fascinating subject and what is their joy. And we'll finish on moving on to Industry 3 and 4, automation, smart machines, and where we are today. And those provide almost unlimited opportunities for mechanical power transmission engineers, and not least the challenges we face on the journey to a green and sustainable planet. And if you thought the challenges we've had over the last couple of 100 years were a lot, that's nothing to what we've got to do over the next few years. So, let's go on a little bit. From ancient times, I've actually dug in the history books, and we go down now to over 4,500 years ago, and we can see this south-pointing chariot, and in there you can see a selection of gears. There's actually a differential gearbox in there, and that was developed over in ancient China, if you like. And just to prove the point, we've been using mechanical power transmission for so many thousands of years, and it's been critical to what we do. Even if all you wanted to do is not get lost in the desert or wherever you were, and make sure you knew where north and south was. Moving on, just over 2,000 years now, we have this little, if you like, navigation device. This is over 2,000 years old. It's the Antikythera mechanism. And what it was just a navigation device using a series of over 30 gears and plates to calculate lunar and solar calendars based on the movements of the sun and the moon, so you can navigate. And this was about 82 BC, and it was salvaged from a ship that sank 65 BC. And this is what people have been doing throughout history. Now, that is mechanical power transmission. It's more to do with motion control than really sending power, but it's just to show the point. Engineers and people have been using these almost as long as we've been civilized. However, what I want to look at now is machines where we're talking about transmitting power. And so let's think about, first of all, machines powered by people. So this is the ancient Egyptian shaduf, as it's called, but all it is it's a water lifting device. And the prime mover is a man, and the driven machine is this water lifting bucket. And what it's doing there, the man is using mechanical power transmission to give mechanical advantage. So the lever is giving him the mechanical advantage, and it's also storing the energy in that rock. So as he pushes the bucket down, he's pushing the bucket down into the water, storing energy into the potential energy of that rock. And so when the water comes up, it lifts it up. We say this is the Egyptian one because the Egyptians kept record of these things. I'm sure other civilizations were doing this. But that is one of the machines where we're using mechanical power transmission. But the motion is discontinuous. And so if we go to the next slide, we can look at machines powered by animals. Now, this is really quite ancient. And it's a camel-driven Persian water wheel. And it's a representation. This is from its history books and whatever, we can see this. But I want to point out a few things. First of all, we have the driven machine at the back, which are water lifting buckets. And those are going at their ideal speed. It's going not too fast so the water spills, but it's going slow enough so as the buckets go through the water, they can be filled. And it's going around in that its center of axis is horizontal, so the buckets go up and down. But the driven machine, the driving machine, the prime mover is a camel. It probably doesn't appreciate this, but it's also at its ideal conditions. It's walking round on a horizontal surface, and it's going at a speed which isn't too strenuous, and so its master can make it work all day to do it, but it's going horizontally around at the speed we want. And that mechanical power transmission is doing a few things. It's changing the direction of rotation. So instead of this vertical axis, it goes to a horizontal axis, is what we want. And also by those pegs and those crude cogs, those primitive gears, it's giving the speed ratio we want. And so that's a key thing we see as we go through history. Mechanical power transmission and gears are letting things run at their ideal conditions. And one thing we take for granted, rotation gives continuity. That's what's happening. Because we've got rotation, unlike the water lifting buckets going up and down, we get continuous motion, which is an advantage we often take for granted. So not only did we use animals and people to do it, we use natural resources, what we call renewable energy now. So we had machines powered by wind, and in this case we had the prime mover, which are the blades going around, and the driven machine, which in this case it's a windmill, it's grinding wheels. So again, we're letting the prime mover blade from their ideal conditions. And inside that windmill tower, we've got a series of very crude gears which have been updated by that Preservation Society in West Sussex there. But it's a series of gears transmitting to allow the blade to go around at their speed, and we can turn the motion through 90 degrees so we can get the grinding wheels going at those speeds. And in that case, we're grinding corn or grain, but also we use wind machines like they were, I wouldn't say windmills, to raise water and to move water out of areas where you could do that. And so again, we're getting useful machines, and the power transmission is, I'll keep repeating it, letting things run at their ideal conditions. We have machines powered by water, and again, we could have grain mills, water pumps, and here you can see that we can have water wheels where the water can come in at the bottom, the middle, or the top. And again, it's the same message, and I'll stop saying it after the next few slides, but the power transmission is letting things run at their ideal conditions and their ideal positions. Okay, so if your mill pond is above you or the river's below you, we can play about with it so we can drive these machines ideally. So this is a quick history lesson. However, one thing's important there. You had to wait for the wind to blow. You had to wait for, or put your machines near where the rivers were, where you could make a mill pond or drive it. And that's not ideal. So man's always inventive. And so we make an engine. Now an engine, the definition of an engine is it's just a machine that's used to convert some sort of energy into mechanical energy that can be used to perform useful work. And this is, again, over 2,000 years old, 200 BC, we have what's called Hero's engine, which is, if you like, the very first steam turbine. What you see vessel A there is a sphere, and that's connected by two pipes, FED, which go into that water container where there's a fire beneath. So you're creating steam, it's going into that sphere, and the two nozzles H and K drive it round. Now, this wasn't ever seriously used as an engine, but it was shown how you could use, if you like, fuel to light a fire to convert the energy into something you really wanted, a rotation. But it wasn't until then, if we move on now, and this is where we're going, until the late 18th century, and where we had the steam engine. And this was it. This was the first practical industrial engine. This was developed, and this is a large engine. And I'm using James Watt's steam engine here because James Watt was the man who coined the phrase, if you like. When we had the first practical industrial engine, we had to create a new word, and that was horsepower. We needed a unit of measurement to rate the power of the machine we got. And he was adopted by James Watt to compare the output of his steam engines with the power of draft horses. It's later expanded to explain the power of all other sorts of engines, electric motors, steam turbines, internal combustion engines. And there's a certain irony here because we've replaced the term horsepower with the word watt and kilowatts. And so the man who invented horsepower, his word he created has been replaced by his name, watt, and kilowatts and watts, and sometimes megawatts, as we'll see on some of the things we see later. So this heralded the Industrial Revolution, Industry 1, and let me emphasize this. That meant we had single machines for many users, and we don't have time to go into how steam engines work, but it's a piston that goes up and down, and you can see here the lever and on the previous one. And so the first serious application was pumping engines. And in Cornwall, where they made the most initial developments of steam engines, They were used to get water out of the tin mines. The tin mines had gone under the sea to collect as much tin as they could, but they were limited by the mines flooding. So we used these engines to pump the water away so we could carry on mining. We call it Industry 1 because it was single machines for many users. So you had one big machine and you using it so many people could work. So we drained the mines, and so we could have many miners digging away at the coal to do that. And that developed into the mechanization of factories. We look at this, a picture from the mechanization of cotton mill. So look closely at this. You see across the ceiling of that cotton mill, you see all those shafts going along and the pulleys and the belts driving individual machines. What we had there were one large machine, a single machine, and there were many users there on that one machine. And this gave us the mechanization of factories. And there's a point here that I'll make. We'll mention at the end of this that there is a gears and gearbox introduction course. But a lot of these history ones, there's a table of references at the back. So if you want to dig deeper into any of these historical photos or historical things I've described, there is a list of references. And I've chosen that list of references so members of the IMechE take advantage of their online library. All of these pictures I've got there, I've got references to books and documents available online at the IMechE library. So if you want to do digging into these things there, the information's all freely available for you to use. Some of the more detailed of the gears and gearboxes, that will be on the later courses. So here we are, and you can see here mechanical power transmission. I haven't shown so many gears here, but it is mechanical power transmission. It's letting the prime mover run at its ideal conditions, and those individual little machines and all those things running at their ideal conditions. So we get mechanization of factories, and that's what's happening. What we sometimes overlook is that with these single machines for many users, not only were the factories there, but you had to transport the products. And so that picture there, Stephenson's rocket. And we developed these rail engines so we can transport the coal we'd dug, the tin we'd got, and transport all these things around. And again, there's one machine, and it's driving a whole lot of carriages with coal on there. And sometimes people as well, and so we could move people about. It was a massive change, Industry 1, single machines for many users. And it did start to transform, if you like, our way of life. Whether that was good or bad, it certainly transformed it. So if we just think about those cotton factories, instead of people working out in the field, they were drawn into the towns so they could work in factories. And it may not be an ideal, but it was a much more reliable source of income than what they were getting before. And so again, this whole way of life, which changed towards the end of the 18th century, exploited and used mechanical power transmission to get there. But then what we call now the technological revolution. Many machines for many users. And what we're saying here is now, instead of one large machine, we had lots of smaller prime movers. And I've shown pictures there of an internal combustion engine, an electric motor. On the bottom right picture there, that's a picture of the steamship's turbinia, where the first steam turbine. Remember Hero's machine? Well, this is towards the end of the 19th century. We had a turbinia with a steam turbine. And this was now really did change it. So we had the smaller prime movers, so we could have many machines for many users. Everybody was getting them, factories using, things were going on like that. And this again, every one of those prime movers pretty much need mechanical power transmission, gears and gearboxes. And this technological revolution came to what we call mass production. And this was towards the start of the 20th century. And I make no excuses. I know that Mr. Ford didn't invent the car, the internal combustion engine and the first car. But the point is here we had mass production. So what he introduced the Model T, and then he introduced integrated moving assembly lines for auto production. So not only did his products have single machines for many machines for many users, we were using these machines to produce them. And a few things we often don't understand, that what Henry Ford did, not only produced these so rapidly, it reduced the actual cost of the product, but it actually gave a step change to the wages of production workers, so they could enable them not to just buy motor cars, but the resulting products. And so this mass production changed again the way of life, because now you would never have believed that the end of the 19th century, within 50 years, almost everybody could have their own personal transport or whatever. So all these things in our way of life came, and each of these machines we're using was demanding mechanical power transmission. Bear with me a second while that moves. Okay, let me go back one. We've missed a slide there, I think. But why mechanical power transmission in gears? Well, primarily, mechanical power transmission systems allow the prime movers and driven machines to both run at their ideal conditions and location. And when I talk about mechanical power transmission, I talk about gears, gearboxes, chains, sprockets, belts, pulleys, levers, and cranks. All these things we've seen in those examples, allowing these things to work. And I promised I wouldn't say it again, but they're running ideally at their conditions. So that's why we use mechanical power transmission. But what about gears? Well, there's a few things about gears which separate them. And there's a table here of all those different things I mentioned there. And that actual table is from one of the BJ teaching packs. We can talk about that much more if you attend the Gears and Gearbox course that's coming up. But we can see there we have spur helical gears, bevel gears, worm gears, and all those things going there, flat belts, V-belts. And the thing is that whilst gears aren't the fastest of mechanical power transmission, that accolade goes to flat belts, which you can run at 150,000 revs per minute. But equally, we can run spur helical gears up to 100,000 revs per minute, and that is an incredibly fast machine. If you've ever been anywhere, a machine that runs anywhere near those speeds. But look at the power density you can get from gears. It's incredibly high. And then the efficiencies, again, it's incredibly good, 96, 99. That's not untypical. Even worm gears, which over the latest years we're getting those to be a lot more efficient than they ever were. They're incredibly efficient ways of doing these things. So all those things exist, but gears give you not only the high speeds, power density, but one thing, again, we often take for granted is it gives you flexibility. While spur and helical gears run on parallel axes, and if you like, belts, V-belts, tooth belts, roller chains, they all have to have parallel axes. That's not so with gears. If we look at the next slide, we can see crossed axis gears there, we can see worm gears, we can see bevel, spiral bevel gears, and even hypoid gears. And the truth is we can change the axis of power any which way we want. Even that camel-driven pump was doing this over 2,000 years ago. But we can change that. And this allowed those small prime movers to get the ideal mechanical power transmission and develop all these things we're looking for. Before I go on, I just want to go on a few things to talk about horsepower. We take it for granted, these things here. And so this is a 1 horsepower machine. Absolutely, we understand that. But that was never enough to do the things we wanted to do. So here we can see a 30 horsepower machine. And I'm not convinced every one of those 30 horses is pulling their weight or doing all those things there. But these were developed. These were developed in the 19th century, so we could feed the growing number of people. That's a 30 horsepower machine. That's from the USA, where they had these very large machines and very large prairies of wheat where they could use it. Again, 30 horses pulling that, and I am not convinced they're all pulling their weight. But if I just go on, that is a 30 horsepower tractor. And so just look at that. That has the power of what we see at the top right there. And all I have there is an internal combustion engine. All I have. An internal combustion engine. Then it has a gearbox in there, which gives you different ratios. Then it has a differential gearbox. Not only is that changing the axis of power through 90 degrees, it's also allowing those driven wheels to go at different speed when the vehicle goes around a corner. In addition to that, we have gears and gearboxes in there, producing, allowing to have power takeoffs to drive things. So whether you like it or not, that tractor is doing all of the work those 30 horses can do, probably more efficiently transfer of energy into the work done, and one man can do it. One man can drive that tractor and do what was doing there by 30 horses. And you can see just by thinking about that, what a massive change in how we manage to feed people. And there's a concept here, which I'm not sure if the figures are absolutely right, but the concept is at the beginning of the 20th century, let me get this right, yeah, at the beginning of the 19th, the beginning of the 20th century, just let me get that right, we had 1 billion people on the planet, and at the end of it we had 5 billion people, and we were farming perhaps not as much land, because 5 billion people take up a lot of land. So in order to feed all of those 5 times as many people, we needed to have these machines. And where that takes us is another issue, but that is what's happened, and that's what we have. So 30 horsepower, that looks good, but just look at this John Deere John Deere tractor. That is a 300 horsepower machine, and that can do the work pretty much of 300 horses. And I believe that people are developing tractors a lot larger and greater than that. Now, yes, it uses a lot of energy. It does contribute to global warming, but if you need to feed those many people, you need to embrace how we do that. And that balance between feeding people and sustaining our planet is something engineers have got to face. That's not what we're here to talk about today. We just think about those things. So let's go back now. Let's do a little engineering thing. It's a key to power transmission, and everybody who's ridden a bike, everybody who's changed gear in a car understands this. Power equals torque times speed. So, and a nice coherent sets of unit. It's that name again, watts. Watts equals Newton meters times radians per second. So if you reduce the speed with the same power, you're increasing the torque. This is the turning moment. What drives those wheels? What drives those machines? And if you increase the speed, you reduce the torque. Now, everybody knows that. Everybody who's ridden a bike knows that. Everybody who's changed gear in a car knows that. But, and this is the point, if you increase the speed, the torque reduces. So the stresses on those machines get smaller, they get lighter and cheaper. And that's what's happening all the time. So, let's move on. Let's go back. Apologize a second. Sorry, let me move on. I hope you're skipping up to the slides. I do apologize about this. So we'll look at personal transport. And again, I'll go through these. There's a lot of slides to get through. But we look at personal. Everybody has access to some sort of car. So look at that sports car there. Just let me explain, take that, what I've just started a little further. There's an internal combustion engine there. And again, that's an Aston Martin car. It's not particularly a David Brown one. But that has a 300 horsepower engine in there. And that's quite staggering. The problem with that, it develops at power at 9,000 RPM, which is much too fast to drive those wheels. If you drove those wheels at 9,000 RPM and exploited the 300 horsepower, that car would have to go 400 miles an hour. And then even an Aston Martin doesn't go that fast. So the point is this: what you need to do is to reduce that speed to something useful, and that's indeed what you do with a gearbox. And I mentioned before, and in order to go around a corner, those driven wheels at the back need to go at different speeds and still deliver torque. So you use a differential gearbox in there. And we actually saw one on that south pointing chariot, but this was developed with cars allow you to do those things. So you can exploit the power of that internal combustion engine and drive that car at fast speeds. On the right, we have an electric car, electrically driven car. And people say, well, I don't need a gearbox in an electric car because of the torque characteristics. That's not strictly true. Not only do you need the differential gearbox to go around corners, but what you will find in electric cars, you will find a single ratio. On the first generation of electric cars, you'll find a single ratio gearbox. To allow that motor to go quicker, you can make it smaller and cheaper because it's going faster. Remember, it's going faster, the torque's reduced, so the stresses are lower. You can make it smaller and cheaper and lighter and run again at its ideal conditions. You do not need, because of its torque characteristics, to keep changing the ratio all the time, but you do need to have that gearbox to run it there. But I have to say, talking to experts in the industry, the next generation of electric cars are indeed having a multiple ratio gearbox in there, even if it's only 2 ratios, just to make them more efficient and able. And we go through all these little things here. I won't labour too long on this, but every part of our life today is driven by machines, gears and gearboxes. We're transporting goods there, water treatment and management, all of those things, whether the Thames barrier or whether it's water treatment plants, there's machines in there doing it. Steelworks, all these activities require gears and gearboxes. Wind power, we'll talk about that in a few minutes, but that's wind power as we go through there. Wind generation, over 90% of the wind turbines you see have a gearbox in there, allowing that alternator to run ideally and the blades to sweep at the right speed. Solar power stations, there you see a 1 megawatt solar power station. I think there's something like 6,000 mirrors focusing the sun's rays onto that collector. In that case, each of those has 2 gearboxes. One is an azimuth drive and one is a tilting drive, so we're always focusing the energy on that collector. Obviously, go into tidal power. There we go. Those are machines which are being developed, and each of those will have mechanical power transmission and gear. So we're using them all the time. So now I'm come to the revelation, and this is where we are. The inescapable truth, and this is from somebody who actually has spent his whole career on gears, is that they're used not because anybody wants them, but because we need them. The thing I spent my life on, nobody really wants them. They're only there because we need them. And there is a secret joy there. I'll explain that in a second. But what I'm saying here is that actually if I had a gearbox, it's no use on its own. It does nothing. It needs a prime mover. It needs a driven machine. And that is a secret joy. And that is what it's. This is the revelation. To fully understand and appreciate gears, one of the simplest, oldest, and perhaps most elegant and precise of all mechanical components, it is necessary to grasp a vast range of engineering topics. And that is where I found the joy, and what I believe the joy is. Because they embrace so many technologies, there's always an opportunity to learn something new. That's what I've been doing for 50 years, and it's inevitable that once involved, you will meet and enjoy working with many different and helpful engineering experts. So now, what I want to do is go through where that joy is. So we'll quickly go through these things. First of all, you need to understand the machines we use. These are the most simplest ones. So for every machine we use, every driven machine, we'll find there's a torque speed curve. And so the one on the top right there, everybody knows it's a fan curve. So the torque on a fan varies with the square of speed. On the left there, we have a vehicle. And so what we have is a rolling resistance, a green line. And then you have aerodynamic drag, which goes up pretty much exponentially, or with the square of speed. And so the red line is what what you need to drive a car or a vehicle to go faster and faster. If you're going to be involved with gears, you need to start understanding all these things here. Also, then you need to understand the prime mover at the other end of it. The one on the left of those diagrams there, you'll all know that if you've driven an internal combustion engine car, the torque peaks as you go up in speed. And so as you go up there, you get a bit faster, you reach a peak torque, and then as you go a bit faster, the torque goes away, so you have to change gear. Top right figure there, this is the value of electric motors, and this is where people get shocked. When you first drive an electric car, you put your foot down and the torque's there straight away. You see that torque curve that goes across there and along, and it fades away to nothing as you've reached synchronous speed of the electric motor. You need to understand these things. And just look at that diagram at the top right. Yes, you understood the maths of it, but until you drive an electric car, you didn't really get the feel of what that really meant. But as I say, the next generation of electric cars will start having a ratio change in there as well. And we've got a steam turbine at the bottom right. I rush through these, but if you're going to start developing systems with gears and gearboxes, you will need to understand. And these are all that straightforward as you look on these simple diagrams. So, just let me go back again, sorry. So we need to understand the system design. So what I've got on this slide here is I'm going to put together a system where I've got, let me say I've got a fan and I'm driving it by electric motor. So I've got two simplified diagrams there, and I'm going to combine those two diagrams on the left to the one on the right. And so we can see the available torque coming from the electric motor, and then I can see the required torque that the fan demands. And you can see there's a mismatch. Only at the rated load do the speed and torques match. And until we reach the rated load and speed, that motor is supplying a lot more torque than the fan requires, which in most cases that's good news, because that additional torque goes to put kinetic energy into the system, so you very rapidly get up to the speed you want to run at. However, if you look at that torque curve there, whilst you're getting up to speed, the motor is developing twice as much torque as you really want, you're rating the thing for. And so you've got this overload capacity, which is great news if it's a light system and you get up to speed very quickly. However, imagine you had a great big flywheel in there and it requires a lot of kinetic energy to get it up to speed. You might spend minutes getting up to speed, and all the time you're overloading the system. Somebody has to put these systems together and understand this. And what I mean by that is that, yes, you could put a fluid coupling in there. You can buy a very smart motor, and you can put in there some limited slip, clutches, or whatever. You get some smart motors to control that. But somebody has to make that decision. Somebody has to understand the system design, put all things together. Okay, so we've done all those things there, but then I need to understand a bit better the loads in the system, and that's what I've got here, a diagram where you can see the loads going up and down. But as you know, loads are never steady, and when you go from one state to the other, you get transient loads, and you need to understand those. And every system, the load is never steady. You need to, if you're going to have a successful system with a gearbox in, understand these things there. And I'll give you an example here. I'll very quickly go through this because this is nice wind turbines. And if you think these are the smoothest drives you could ever imagine, this is absolutely not true. This is going back to 1984 when we had the first of the contemporary wind turbines came on board. And people were shocked and amazed at the loads that were happening. Blades were falling off wind turbines. It is one of the most arduous applications that people had come across, and nobody expected it. We had massive amounts of failures, both for wind turbines and all of the transmission systems were suffering load nobody understood. So what we had to do is go and understand it. And yes, you've all done this at college, and you write the equations of motion, and you solve these differential equations of motion, and you can predict what the loads are. So all that time you spent in maths learning about Laplace transforms, yes, it's really useful. You need to understand the system. I was very lucky. One of our engineers, Ian Pate, could remember how to do these things, and Ian managed to do this, and we quite suddenly found out there was a lot of things going on that system. And I'll quickly say, on that diagram you can see there, we start at the top left of the hub, go through that series of lumped masses, until eventually you connect to the grid. And what we find out as soon as you do this analysis, actually the stiffest, most unforgiving, rigid part of that system there, and for a mechanical engineer this is sometimes a shock, is that air gap between the rotor and the national grid. Because in this case, that is unforgiving. And just let me go on to the next picture. When we actually went to measure these loads, and you can see there how even under steady state, that's a measure of the bottom's wind speed, and in the middle we've got power and we've got torque. You can see even when you think it's steady state, it's nowhere near steady. That was a 330 kilowatt machine. And what was happening is you were going through there, we were getting typically up to 450, 500 kilowatts going through the system. The biggest shock in the system was there as you brought it up to speed. Yes, this is Altamont Pass in California, 60 hertz. 60 hertz is the national grid in America. Yes, the machine's running at 60 hertz. However, if you were absolutely in phase with the grid, you certainly were a couple of milliseconds later, because that was the stiffness of that last part of that diagram there. It would grab you, and whatever loads was necessary, it would bring you into phase. And that's what people learned, and that's what caused a lot of failure. So, understanding the system, sometimes you need problems to fully understand these things. But over the years, wind turbines, we've learned a lot. 40 years since that started happening, and now things are pretty reliable. Still very arduous application. Once you know the loads, you've got to manage them, and I need to speed along a bit there, but there we go. You look at the gear teeth, we can see the Hertzian stresses there, we can see the bending stresses, and we need to do the stress analysis. And this is, yes, all this metallurgy you've learned, you can look at all these things, and all those illustrations there are from the British Standard on identifying failures. We can see pictures of bending and whatever. Too much contact stress, the Hertzian stresses come at the root of the teeth, just below the surface. The cracks propagate from just below the surface, so we get surface pits. And again, we go on. And we need to calculate, we need to embrace the standards and calculate the load capacity of spur and helical gears. And that's what people are doing all of the time. And today you have little or no discretion. You need to follow the standards to make sure you get certification for the products you use. And these have been developed over the years. Just going into this is where engineers have to come make the decision. The massive principle in all of these gear rating standards is to start at the top, where you work at a nominal tooth root stress, sigma F naught. The detail of this we can go to in the gears and gearbox course, but the concept I want you to understand here is you don't just sit at your desk and say, that's the nominal root truth stress, that's what it's going to feel. You have to make a decision on how it's going to be manufactured, how it's going to be installed, and how it's going to be maintained. You need to go and discuss with your manufacturing people what accuracy they can get. You need to know what application factors are there. So the engineer isn't just sitting there giving a theoretical thing. He needs to go and understand, and then he will modify that nominal stress to give you the actual stresses in there, taking account of the accuracy of manufacture, the application factors like we saw in that wind turbine, all those things there. And then you make an engineering decision to say, that's my theoretical thing, that's what I think I'm pretty certain is going to happen, so those are the stresses we have to accommodate. So again, I'll go through that. There's allowable bending stress, all of that Goodman diagram, all that fatigue data, because pretty quickly with gears you get up to infinite life, you soon do 1,000,000 cycles, and so you have to understand all that thing you learned about strength of materials. And again, you can get surface damage. Gear teeth are always a mixture of rolling and sliding, so you have to depend on lubrication to do that. And there's more and more standards. I'll make the point about standards. This is ISO 6336, and you can see that we're now up to part 22. There's 22 sections to that. And if you're young and involved, if you're not happy with the standards, please get involved with the UK's standards committees so you can attend ISO meetings and put your 2 pennies in to say, this is how I think the standard should be, this is how we need to improve things. There's opportunities there to do it. Tribology and lubrication, we need to separate the surface. So you need to understand about hydrodynamic, oil films, elastrohydrodynamic, mixed film, all these things here. You need to understand this. And now we can calculate pretty accurately oil films. And we rely very much on the oil companies to deliver and give us the additives and lubricants which allow us to make gears run at incredibly high speeds and loads that we wouldn't have thought were possible 50, 60 years ago. Thermal issues are important. There's always a power loss, even though we know there's 99% efficiency in these things. There's still a lot of heat to get rid of, and we need to look about how the coefficient of friction changes with these different lubrication and how we're going to get rid of the heat. Yes, bending moment diagrams, shear deflections are important. We need to know how things change. Material specifications. We're very lucky. Now the materials we get are incredibly strong, but you need to embrace the metallurgies. This is from 6336. In order to get a gear material which will do what you want it to do, you have to get certification. And so what you need there is certification, and there's 14 parameters you have to certify and prove before you can get a piece of material. Luckily, we have some wonderful material suppliers now who can supply material with the appropriate certificates to do this. You need to harden the gears to get the thing there, so heat treatment is very important to you. We can nitride gears, we can carburize and case harden, induction harden them. Give us a surface hardness we want, and say is metallurgy incredibly critical to what we do. Material science. I hate to say this, but metallurgy and treatment are critical to the performance of gears. So those metallurgists you work for, every successful gear company must have successful metallurgists and heat treatment facilities, because we rely entirely on it. So all that you learn about material science, and once you start visiting a heat treatment plant, you'll fully appreciate metallurgy much more than any classroom will do. Noise and vibration, again, that's an unavoidable truth. Unless you properly manage gears and gearboxes, they can be a significant source of noise and vibration. So managing the source of vibration is important. And just look at the loudspeaker. I give this example because noise is produced because you put a vibratory force into a diaphragm. The loudspeaker has a diaphragm. And the truth is that gears will produce vibratory forces. And because there's a torque reaction, those vibratory forces will go to earth through the structure. If any part of that structure acts like a loudspeaker diaphragm, it will produce noise and vibration, which can become unacceptable. So, managing the system response. It isn't just the stiffness, you understand the mobility of the gear case and the structure. And what I mean by mobility, it isn't just the stiffness, it's the frequency response. And that gearbox there, that courtesy of David Brown Center Solo, that gear case is tuned so it has pretty much zero mobility at tooth contact frequency and all those things there. And again, that's what you need to do if you want to make gears which don't damage hearing or cause a nuisance. Managing the system response. Campbell diagrams. Not only do you have to avoid torsional natural frequency, but also transverse natural frequencies, which you will get at high speed gearboxes in in journal bearings, where you can see these things bouncing up and down, you need to do the calculation to make sure you avoid resonant conditions. I am going through these quite quickly, so we have a little time left for questions. Transmission error. Transmission error is a measure of the source of gear noise. And that is, we model gears, we put a two stiffness, and transmission is how much that representative spring connecting two bodies moves during the transmission. If that's zero, you get no noise. But these days, we have to predict how the stiffness changes as we have different gears going into mesh. That was a massive mathematical challenge for many years, and now we have software which helps. But in order to make silent gears or very quiet gears, you have to do that calculation, embrace that. Which leads me nicely onto metrology. I say that gear teeth are amongst the most elegant, precise and accurate mechanical components. I'm showing there some standards there of typical gears we make, and you can see there that we have to measure pitches by down to 2, 3, 5, 6, 7 microns, and even a pretty crude grade 7 gear is expecting manufacturing tolerances the same size as white blood cells. That's how accurate these gears are that we make. And people take this for granted, but any gear you see is incredibly precise. We're scrapping gears if they have errors in profile, pitch and lead, which are no bigger than white blood cells. So you have to have incredibly accurate gear measuring kit. And so we have to make the gears. Quickly get our notice time is running out, but there's many manufacturing options. We can form gears, we can cast gears, we can machine gears. All of manufacturing are options and are exploited by these things here. Machining, let me talk about this, because one of the great values of the Involute gear is we can make very accurate gears with very simple tools. And you can see that straight-sided rack cutter. On the left, it's one that goes up and down and cuts a gear shape there. On the right, it's representative. If we made that straight-sided rack and rolled it with some modeling clay plasticine, it would produce a perfect involute shape. And for over 200 years, that's been a massive advantage. What it means is we've had the ability to make incredibly accurate gears with very simple tools, and you could sharpen them and still make them. That has all changed with the advent of digital machining options. We can now use 5-axis, multi-axis CNC machines. And so the options to machine gears are increasing all of the time. Forming options, this is from IMechE, where you can form gears using sintered, and so you can take powders, put these together, make a green thing, then you sinter them at high temperature and produce very dense gears. It will never be as dense as forged gears, but this is an incredible option. And today people are producing gears with very clever arrangements of powders in there to dampen noise, to dampen things like that, and still have significant power capacity and produce gears incredibly cheaply. Additive manufacturing gets more and more important. The picture there, the first additive manufactured gears the BGA had made 15, 20 years of 15 years ago. And I ought to mention I am focusing a lot on metals here at the moment, but actually forming most of the gears I guess in the world are made of plastic, and so we use similar ways. Generally what we tend to, and just so I can explain this properly, if I go back a couple of slides here, if we look on this manufacturing options here, casting and moulding are the ones used pretty much for mass production, and plastic gears come into casting and moulding. Forming, yes, maybe. Steel gears tend to go in the machining centre on the right there. But if you want to mass produce gears cheaply and quickly, you need to invest heavily in dies and injection moulding. You don't do it for a one-off. And so there are differences between plastics and steel manufacturing, but the world is changing. And the powder metallurgy is giving some very exciting options. And the forming options, incredibly. As I was saying, it's 20 years ago we found the first additive manufactured gear. Even as we speak, there are people putting together some collaborative research projects so we can do some pulsator testings on some additive manufactured gears. Over the last 20 years or so, these additive manufactured gears have got very strong, and so hopefully over the next 18 months the BJ will be doing some collaborative research with members from industry to test how strong these gears are. And you can see that I've just picked up some papers from the IMechE over the last few years. This is going to become increasingly important. So now I'm on the last 4 slides, and I do apologise for rushing through these things. I want to talk a little about Industry 4. And yes, I've done all the history lessons. I've gone through all these things there. But the amazing thing is, as we approach Industry 4, things are happening in our industry. First of all, I want to talk about smart connected products, the Internet of Things. We've talked about it for a few years, and one of the first people is, again, I won't mention this company again, but David Brown Santasalo, have this gear watch system. So now we can embed onto gearboxes around the world. This is Internet of Things. It measures what's going on in the gearbox. It goes to the internet. It goes through a secure network. It goes to the engineer who's sat there. She's sat there looking at this, and she can monitor things. It's been going on a few years now, Internet of Things, and so it's making the things change significantly. The next item is digital twins. Digital twins is something, and this is from, again, Newcastle University, where look at the theoretical tooth flanks. What we've got on the left of that diagram are measurements. Remember, we're measuring the surfaces of gears to the level of white blood cells. So the top 2 diagrams on the left are showing the theoretical tooth flanks. And if we go over to the right, then we get the theoretical flank contact stress distribution. And this is what's happened at the design stage. We've worked out the theoretical tooth flanks, and we know that if we get that shape of gears, those are the contact stresses. But what's happening in this application here, we're measuring the tooth flanks, and it's saying, well, hang on a minute, that isn't what you designed. There's some errors there, and on the right there, we're getting the measured contact stress distribution. So this is the design unit. One of the Dontine system there is used to calculate that stress distribution. It's saying, hang on a minute, you thought you were going to get those stresses, those errors are giving you this. And I know that digital twin, which we're using there, is allowing to put that knowledge into the machines doing it and saying, hang on, well, if you want to make that, reduce those stresses, it's learning and it's remachining to get rid of that. Can't machine it too much because you get rid of all of your surface hardness. So those things are going on even as we speak. And the one last slide I want to fit in, which is perhaps one of the most clever ones, which is machine learning. Here we've got a smart oil plug put into, this is a rail gearbox. And so there's, I think there's 40 of these plugs, and these plugs look after accelerometers, temperature, and oil debris. Now, this isn't just recording these and sending them back. This is doing, it's machine learning, and what's happening, it's going through understanding what's going on. And this final slide should show it. And this machine learning, it's a self-organizing map. And as that plug is sat there, without human intervention, it's learning from what's going on. And so I said it took me a long time ago to understand the Laplace transformations to solve differential equations. I'm not even going to try and explain the neural networks that this is happening. But what this smart plug is doing at the moment, it's going through this whole fleet of rail gearboxes, measure, and even as we speak, it's quite scary that it's learning about it. And so it's like, hang on, I've got this measurement here, and I know that's a deviation from gear tooth profile. I know that's insufficient gear tip. It's picking up these things. And this is the company called Transmission Dynamics is working on these incredibly clever things. And I find that quite spooky. This is a machine learning things all of the time. Yes, humans are there involved in setting it up, but it's learning on its own, going its own merry way and finding out these things. So I'm going to finish up now with a great deal of relief around the room, I understand, but what I want to go through is that I started off, and this is the additional references, this is the pictures here. I started off nearly 4,500 years ago with a south pointing chariot. I've gone all the way through all of this mechanical power transmission, how gears and mechanical power transmission, and I finished off with the Internet of Things. I finished off with digital twins and scaled out. I've ended up with a gearbox with a plug in there that's learning all the time of what's going on. And I actually wish I was starting my career again, because the opportunities which are coming our way are quite exciting. All those things which you've got there. So, and I'll finish now. I'll just say additional references there. You can access pretty much all of these through the IMechE library. The Gears and Gearbox Introduction course Dan's going to talk will dig a lot deeper into everything else you've seen. And if you want to know about anything in between time, please get in touch with the IMechE or back to me, and we can get you in touch with any of the topics I've covered. So with that, I'll hand over to Dan. And I'm sorry I haven't left that much time for questions, and I have rushed it a bit. But Dan, if you can step in and start talking, and if you picked up any questions, I'll be more than happy to answer them.
Yeah. Okay. Look, I'll let you get your breath back there, Graham. But that was an excellent webinar, and we have overrun on time slightly, but that's because such amount of information there, and there's so much more to probably be able to give within this. So yeah, I mean, if you are interested, people are interested, then we do have our Gear and Gearboxes introduction course coming up. I'll put the link up there. So if you are interested in attending this and finding out more and going into more depth with Graham on this, then obviously signing up to this course is something of interest to you, then I will be putting the link up there. And you may have already seen that in the chat box. What I think we might try to do, we'll answer a couple of questions shortly. And whilst we're doing that, if anybody else wants some questions, put them into the chat box, and what we'll do is we'll put them into a document, these questions, pass them to Graham to answer, and then we'll put them onto the LMS for you to review that document and have those questions answered, and you can review them that way. So we think that might be a suitable option, because obviously we're conscious of time and a lot of people may be having to go now. But Graham, I've got a sort of two or three, a couple of questions here maybe. Have there ever been gears which were actually coated to help strengthen at all, Graham?
Oh, absolutely. Yeah, we could go a long way into this. I rushed over. Most of the gears you'll see transmitting a load will have case hardened or a hard case on there. But yes, there are a lot of coatings we've tried. A lot of coatings we've tried to do lots of things. If I go back when I first joined, we had chrome plate on there, and we did things. But over the last few years, there's been some very exciting developments of different things we can put on there. And at the British Gear Association, we did some collaborative research, and there are results about, so we can show how the performance of gears can be improved. And this was particularly important over the last few years, because one of the victims of our success, over the years we've learned to understand about pitting and bending, and we started putting a lot more power through gear pairs. And because we were designing them better materials. But what happened is we put more, there was new modes of failure came, and one of these was micro pitting, and that's a polished surface which arose. And so we looked at various coatings, and there's a lot of suppliers out there who coat gears different ways, and we did some collaborative research. So if anybody's interested, can you send the contact and we can see what's freely about. It is collaborative research. Some of the results are in the public domain, some are, but there are some very good coatings about there which can significantly alter it. And sometimes we use these for running in, but I think where people get a little, I always get a little worried. We didn't spend much time on it, but we can on the course. Gears always need to be separated. And if you're transmitting any significant amount of power, you need a lubrication there. And you need the lubrication not only to produce the oil film to separate the surfaces, but most of the oil you put in a gearbox, most of the lubricant, is not just to separate the surface, it's to get rid of the heat. So if you've got some small motion control applications, yes, you may not be generating a lot of heat, and maybe you'll get away with just a coating. But the datum I'd always start with, you always need lubricant in there to separate the surfaces. You use lubricant and coatings, chemical coatings, whatever it is, to improve the performance, but you also need lubrication there to separate the surfaces. So yeah, there is lots of very positive coatings about for the right application.
And I think actually, Graham, it's actually important to note that the feedback coming in is your passion for this subject area, and the presentation you've given has been, the comments are coming in thick and fast as to how interested they've been, and again, as the passion you brought to this. So thank you, Graham. Another question's come in. Will the involute profile ever be replaced by a superior profile?
Oh, well, there's certain people on there say it's never been the best, but it is pretty much dominant. And it's dominant for 2 or 3 reasons, one of which it was always been very easy to make. Secondly, and this is to get into the detail of it, with involute gears, the center distance can change and the velocity ratio doesn't, which makes gears a lot more silent. But there are certainly stronger gear profiles there. The Novikov conformal gear pair, where you have a concave gear and a convex gear, is nominally and theoretically much stronger because you have conformal surfaces, the Hertzian stresses reduce, and because you have a bigger section modulus at the root of the gear teeth, the bending strength increases, so it is inherently stronger. The problem is that if the center distance of the gears change, the velocity ratio changes, and it may only be about by microns when it changes, but it can produce excessive noise and vibration. But there are some applications where people use conformal gears where load carrying is overridingly important, and certain helicopter applications where people were using conformal gears, non-involute gears, until quite recently. Now, the world is changing. Because we have CNC manufacturing, you can exploit these. And I know there are some gear shapes about, and people are doing development on, where the addendum, which is the tip of the gear, may have a convex shape, and the dedendum might have a concave shape because of the CNC machine you do. And you can tailor these things, so the opportunities are quite immense. So for the moment, I guess the news is most standards are written around involute gears, but that doesn't mean they're the best. They will always be the best. Just because there aren't any standards there are massive opportunities, and these things are happening. So yeah, and I'll go back for clocks and watches where you need gears with large ratios. We use cycloid type gears there. Again, not massive power transmission, but they're much more useful in motion control and clock mechanisms where perhaps noise isn't so important. So yes, there are alternatives people have always been using, and the opportunities are getting greater. But there are certain reasons why the involute is almost preeminent.
Okay, lovely. Thanks, Graham. Okay, I'm conscious of time, obviously, and I think, as I said before, what we'll do is we'll collate a number of the questions that have come in, put them onto a document and put them onto the LMS. And if you can answer them, Graham, over the next few days, and people will be able to access these answers. Just one final one then, relating to the course that's coming up, Graham. Does the course cover fitting or meshing tolerances between gears?
Meshing tolerances, yes, it will do, because what we need to do is it's a very good point there is when you make gears, yeah, we can go on for half an hour on this, but I won't. Yes, it will do, because during the third part of it is manufacturing. We're talking the course is in three sections. First of all, there is gears, and we'll start about the law of gearing in the involute tooth shape. Then we'll talk about controlling noise and loads, making sure the gears will last. But the third section of the course includes manufacture, assembly, and installation. And so the point is, yes, we'll make gears very accurately to the tolerances of white blood cells, but then you've got to install them. And so then you've got to align things properly. And we will certainly talk about, when you say meshing, is to make sure the gears are properly aligned, not only during manufacture, but also they stay there and you can manage distortion. And we used to measure this, or we still measure this a lot with Engineers Blue, but now there's some very sophisticated ways to measure it with strain gauge and whatever. But yeah, and there's certain gearboxes which we will mention in there demand not only geometrical measurements of the gear teeth, they will demand you record meshing checks or what have you to make sure the gears you are fit for purpose. So yes, that will be. And the point is, during those courses, you can ask these questions anyway and get answers to them, even if it's not directly covered.
Wonderful. Okay. Again, Graham, I think you ought to know that the message is coming in. Thank you so much for a fascinating presentation, such a detailed presentation, an excellent presentation. Loud applause here for you. So these are all the messages that are coming in. So
we just need to spread the joy. Spread the joy of gears.
Exactly. Well, okay, I'll wrap it up and say thank you very much for everybody who's managed to join on to the webinar this afternoon. Thank you very much for your attendance. Again, you'll have had the links from future and upcoming webinars, and also details relating to the introduction to gears and gearboxes course that Graham will be looking for to deliver in May this year. Okay, so anything else further from yourself, Graham? Or
no, I just apologise for overrunning. I shouldn't have tried to squeeze too much in. I'm sorry.
No. The delegate list, it didn't go down. And the majority of people stayed, Graham, which is always a good sign. So that's really good.
Okay, thank you then.
All right, thank you very much, everyone.